Okay, welcome back. Before we have been talking about the hash tables, we also show you how to define a hash table, also create a hash table and insert. We also mentioned that for the hash table we introduced before may have some problems, especially when we create so many overflow blocks. And when we have so many overflow blocks, the performance of the hash table will be degraded greatly, right? And we also analyze why it will be degraded. Because if we have so many overflow blocks, it will reduce this hash table to the linear list, right? For storing the key and the pointer pairs. Here we want to further go deeper to analyze why this problem can happen. And can we address this problem besides creating the overflow blocks or not? So according to the previous discussions, the hash table works in this way. Give a search key via a hash function. We can project the search key to some numbers. This number denotes the index of the buckets, right? The main problem in this hash table is that this hash function is predefined and its bucket is not predefined. The number of buckets we can have in the hash table is fixed. It's predefined. Now here we have only 4 buckets. During the runtime, no matter how many key pairs we plan to insert into the hash table, it cannot increase in the bucket numbers. In other words, the depth of the hash table is fixed. We cannot grow the hash table in a vertical way. It's predefined. Therefore, if we further plan to grow the hash table, we have no choices, have to grow the hash table in a horizontal way instead, right? By creating overflow blocks. If we grow in a horizontal way, in other words, we can create a very fat hash table. This hash table can be very long. It just reduces the hash table to a linear list in each bucket, right? Therefore, we may wonder if we have any options to grow the hash table in a vertical way to make it thinner and taller, instead of growing in a horizontal way. We plan to grow it in a vertical way. Is it possible or not? In other words, we wonder if we can make this number of buckets available be flexible, which can be growing during the runtime of the system. The answer is yes. Besides the hash table introduced here, we also have another hash table to be introduced. It is called the Extensible Hash Table. Normally, the Extensible Hash Table allows the hash table to grow during the runtime of the system. It can avoid some performance problems. Here we have some changes. We assume the input keys is some binary codes. Before we mentioned the keys can be some charts, right? But here for the presentation convenience, we assume the input keys will be some binary digits. And K is the longest input key digits. How many digits we can have for the input key? So given a binary input key with K names, so the maximum number of different numbers it can denote will be 2 to the K, right? In other words, we can have some values or numbers in the range from 0 to 2 to the K minus 1, given the input digits with K names. However, for the extensible hash table, instead of directly using all the K binary digits, we propose to use only a bunch of or a subset of these digits to define both the buckets as well as the hash function. How can we do this? So in the extensible hash function, we will define the hash function as follows. We use the first I bits or digits to define the hash function. This I is a number. Normally, this I is smaller than K. We don't use all the K digits. We only use the first I digits for define the hash function. We provide you with an example. This assumes we plan to build a hash table. We predefine the number of digits for input keys equals to 4. In other words, the maximum key length will be 4. We know this in advance. Instead of using all the 4 input binary digits, we define a hash function with only the first 1 digit only. In other words, with 1 digit, we define 2 different buckets. The n equals to 2 denote the bucket numbers. This I denotes how many digits we use for define a hash function. both the hash function and the bucket will grow as the system runs. And based on this data, we provide you with the example of hash tables as follows. So this part denotes the buckets we have. And the left-hand side actually defines the hash function. This part denotes the hash function. Given a key, input key via the hash function, we can map them directly to some buckets. However, here we don't use all the input keys. We only use the first I bits in the key as the input for the hash function. I hope you can follow me right. Before this hash table, we use all the input keys via the hash function. We can project them to some of the buckets. However, for this extensible hash table, we only use a subset of an input key for defining its hash function. We use the first I bits of the key for defining its hash function. You can follow me right? So now we can give you an example. Now here, if we plan to insert a key and a pointer pair, the key we have is 0010. For this extensible hash table, we only use the first bits in the input key. According to our hash function, given the first bit is 0, we know this 0 should be projected to the first bucket. In other words, via the hash function, we map this first bit to this bucket. Right? Inside the bucket, we have two entries. We can store two different entries. And we put this 0010, this key and a pointer in the first entry. Similarly for the second bucket, we can also store the 1011. Via the hash function, we know the first bit, it can be projected to the second bucket, this bucket. Right? We can put this key together with the pointer in this bucket in the first entry. And in the bucket, after it, we also have one entry indicating how many digits we are using in defining its hash function. Here we have I equals to 1, therefore in this bucket we will have a tag. This tag denotes the first I bits are used in defining the hash function as where the buckets. We have a separate this tag for each of the buckets here. I hope you can follow me right. Okay, so based on this extensible hash function, we can do both search as well as insertion. We can show them in the following pages.